Quantum physics is holistic. The observer is part of the system being observed, and the very act of observing a thing changes it. This is why physicists speak of quantum particles as being webs of interrelationships rather than solid little balls of matter. Any action in one part of the system reverberates throughout the whole web. The double-slit experiment allows us to see this phenomenon in action. Here is how the experiment works. Imagine a metal plate with two narrow slits in it, one or both of which can be open, depending on the setup of the experiment. These are the slits that an electron gun will fire electrons through, one at a time. After passing through the slits, the electrons will travel a short distance to an electron-sensitive screen, where each individual electron will land and be registered as a dot. When a great many particles have passed through the slits one at a time, a pattern will build up on the detector screen. Before we look at that pattern, it will help if we look at what would happen if this experiment were carried out in the macroscopic world, using tennis balls instead of electrons. If a ball launcher fired tennis balls at a metal plate with two slits in it, both of which were open, some of the balls would pass through the first slit while others would pass through the second, and still others would hit the plate itself and bounce off. Those that made it through would travel a short distance before hitting a wall, where they would leave a mark directly behind the slit they passed through. Let's say the balls were covered in wet paint. That is the pattern we would expect to see if electrons were tiny balls of matter, but that is not the pattern that actually builds up on the detector screen. Instead of two stripes, one behind each slit, we get multiple stripes with gaps between them, where very few electrons are registered. According to classical theory, it should be impossible for this to happen. This pattern doesn't resemble that made by the tennis balls, but it does look exactly like the interference pattern produced when two waves interfere with each other. A familiar example of this is water waves. When an incoming ocean wave meets an obstacle like a harbour wall that has two openings in it, the wave passes through the openings and then breaks up into two new waves, which then begin to spread out, colliding and interfering with each other. When two waves collide, their energy is combined. Peaks are added to peaks, forming even higher peaks, and troughs are subtracted from troughs, forming deeper troughs. A peak and a trough cancel each other out. But in the double-slit experiment, this same interference pattern builds up when single electrons are fired one at a time through the two slits. The gaps between the stripes, where few electrons land, correspond to water waves that cancel each other out, and the stripes themselves correspond to waves that combine to form higher peaks. So what is going on? Are electrons more like tennis balls or water waves? The surprising finding for physicists was that they are like both, acting like tennis balls on some occasions and water waves on other occasions, depending on whether one or both of the slits are open. If both slits are open, electrons will behave like waves, but when only one slit is open, they will behave like tennis balls. Physicists grappled with how this could be. It is easy to understand that a wave, like an ocean wave, could pass through both holes in a wall at once, since a wave is a spread-out thing. But the classical materialist notion of an electron demanded that it be considered as a particle, even if it did also possess some wave-like properties. Physicists therefore expected each individual electron to go through only one of the two open slits, not through both of them at once. According to the materialist view, an electron would have to go through only one slit at a time, like a tennis ball, and never through both at once. Remember, the interference pattern is obtained when only one electron is fired at a time, so the pattern is not caused by interference with other electrons. An electron is fired. It presumably travels through one slit or the other and arrives at the detector screen. Then another electron is fired, and so on, until enough electrons have been fired to build up a pattern on the screen. But how do the electrons know where to land to build up an interference pattern that would only be appropriate if they were waves? Physicists don't know, they only know that it happens. But this isn't all. Not only does a single electron, traveling through a slit on its way to land on the detector screen, somehow obey the statistical laws of distribution that are only appropriate to waves, it also seems to know whether one or both slits are open. Remember, if one slit is closed, the pattern produced will not be an interference pattern. It will just be a single stripe, like that made by tennis balls. How the electron knows whether the slit it doesn't pass through is open or closed is a mystery, one of the central mysteries of quantum physics. And this still isn't all. While running the experiment with both slits open, physicists have tried peeking to see which slit the electron goes through. They do this by placing electron detectors at each of the two open slits. These detectors register the passing of the electrons, but do not interfere with them, so according to classical theory, they should let physicists know which slit the electron went through without affecting the final pattern. But that is not what happens. As soon as detectors are introduced at the slits, the electrons behave like tennis balls once again, even when both slits are open and the interference pattern vanishes. The electrons seem to know not only whether one or both slits are open, but whether they are being watched. Even an electron, Seth remarked, knows it is being observed through your instrument. Electrons know if someone is watching, then, and adjust their behavior accordingly. Or, put another way, an observing physicist's conscious awareness of which slit an electron passes through changes the way it actually behaves in physical reality, forcing it to change from a wave-like thing to a particle. Remember, quantum systems are holistic, so the observer, just by observing, interacts with, and thus affects, the probability wave, causing it to collapse into a physical particle. The observer and the object perceived, said Seth, are a part of the same event, each changing the other. This interrelationship always exists in any system of reality and at any level of activity. In Seth's terms, reality as a whole, or all that is holistic, like a quantum system, and any action in one part of the system affects all the other parts. So, a physicist's observation of a probability wave affects both the physicist, who becomes aware of an electron, and the wave, which collapses into that electron. Note that the physicist never actually sees the probability wave itself. She can interact with it and cause it to collapse into a particle, but she can't perceive it directly. This is in close agreement with Seth's theory, where what Seth terms action corresponds to the physicist's probability wave. Action, Seth stated, cannot be caught and held, and the nature of perceiving an action changes the very nature of the action itself. Since perceiving an action is itself an action, the perceiving must, because of its nature, to some extent distort the object of perception. Again, in this distortion we see the creation, however minute, of a new reality. Any perception instantly changes the perceiver. It also changes the thing perceived. Like Seth's action, the probability wave associated with an electron cannot be caught and held, and it can never be seen directly because it is not a physical wave. It contains no energy in physical terms, so it can't be measured. In our reality, we can only see the probability wave of matter after it has already entered physical reality through the act of collapsing into a material particle like an electron. Before that time, while still in the wave state, which is to say in the state of Heisenberg's potentia, or in Seth's probable or inner reality, the electron exists simultaneously in every location that would be possible for it if it were physically real, and with every possible momentum, so that the electron is literally in more than one place at the same time. It is, in effect, everywhere in the universe at once, including in both of the slits. This allows an electron, so long as it remains in potentia and has not been observed, to occupy both slits at the same time and interfere with itself. This state of affairs cannot be translated directly into physical reality and must remain in the state of potentia. But its effect is real and can be observed in the distribution pattern of electrons. To become physical, a choice is forced upon the electron. Physical reality demands specificity. The electron must be one thing or another, and in one place or another. Physicists can therefore never physically see an electron behaving as a wave and passing through both slits at the same time. They never see both detectors going off at once, for instance, and must infer the existence of the wave state from the pattern that builds up on the screen. Along these lines, Seth stated that action itself cannot be directly perceived, but its effects upon camouflage can often be perceived. Because physicists can never see the probability wave itself, whenever they do attempt to look at it by using detectors, it always collapses into a definite particle. But if they don't look, by removing the detectors, the electron behaves once again as a wave, but a wave whose existence lies within the realm of potentia, or probable reality, and cannot be physically seen, only inferred. The upshot of this is that when there are no detectors, physicists cannot say that an electron goes through a particular slit. It goes through both at the same time. And this, again, is not due to any limitation of the physicist's equipment. If no one is looking, nature itself does not know which slit the electron goes through. Physical reality does not exist in that kind of objective way. Instead, nature keeps all her options open, all her probabilities open, for as long as possible. The strangest thing, writes astrophysicist John Gribbin, about the standard Copenhagen interpretation of the quantum world is that it is the act of observing a system that forces it to select one of its options, which then becomes real. This is what physicists mean when they say that a conscious observer creates the reality that they observe. Before someone looks, electrons don't exist as physically definable particles at all, but only as a cloud of probabilities in the state of potentia. And it is this cloud of probabilities that produces the interference pattern that is observed. It is caused by the interactions that occur between the various probabilities within the wave. Although Seth's concept of inner or probable reality corresponds to Heisenberg's state of potentia, it includes more than just the states of electrons. Probable reality includes all possible events of any kind, mental or physical. According to Seth, any event that involves a conscious decision exists in several probable forms or variations within probable reality, and any of these variations can, at least in principle, be physically materialized, although, as with electrons, some are more likely to occur than others. Just as a scientist's conscious choice of experimental setup determines whether an electron will appear as a wave or as a particle, so too can an individual's conscious beliefs, intentions, and expectations influence which of the various probable events available to them will be made physically real. A given belief or expectation influences action, making certain probable events more likely to occur than others. A change of belief or expectation alters the probability. This influencing of reality through conscious intention is a central tenet of Seth's theory of reality and is a testable hypothesis, the first we have come across so far. It has in fact already been tested by Dean Radin of the Institute of Noetic Sciences in a version of the double-slit experiment that involves conscious participants, to which we shall now turn. The influence of consciousness on the double-slit experiment. The only way to measure a quantum system is to observe it, but the double-slit experiment showed that the very act of observing a quantum system changes it. An unobserved system simply cannot be measured. This led physicist John Wheeler to comment that no elementary phenomenon is a phenomenon until it is a registered or observed phenomenon. Useful as it is under everyday circumstances to say that the world exists out there independent of us, that view can no longer be upheld. Physicists refer to this situation as the quantum measurement problem, or QMP. It is considered a problem only because many physicists remain uncomfortable with the idea that an observing consciousness should be necessary for collapsing the wave function and thus bringing a particle into physical and measurable existence. Seth maintains that consciousness does indeed create reality in just this fashion all the time, and that our conscious intentions and expectations constantly influence which of the events within inner reality become physically real.